proposal, like anybody who wants to take a nap or wants to go on Facebook, go outside and take a nap, you won't get points off. But otherwise, you know, I did prepare this, so I hope you guys can pay some attention. So anyway, there was no homework. Anybody who checked? Housekeeping. A bunch of you have asked me informally here and there, I want to ask you some questions. It hasn't happened. So between now and the end of the course, if anybody wants to reserve some time, half an hour with me on the picnic benches outside, just grab me and I'll reserve time and I'll have time to talk. If nobody does it, it's fine. I won't be offended, but I just want to know, I want you to know that it's available. So we have Monday, Tuesday, Wednesday, Thursday. All of them are going to be pretty full with other things, like working on incubator stuff and rehearsing and all that stuff, but I'll make time if somebody wants to do that. Another thing about the incubators, the presentations is, you know, I think in addition to working on preparing the content of the presentation, you know, I think it would be interesting and useful to prepare the delivery of the presentation. So, you know, I think in each case, again, each person with their teams, we can not so much rehearse, but talk about who should speak and the ordering and so on, because we do have a pretty interesting crowd coming, including people that might be future employers and people who might give references. So it's probably worth, you know, putting our best foot forward. And remembering what I said the other day, which is people never notice if a demo doesn't work the way you think it should work. So once we do our best to get it there, then the next step is going to be mind over matter. And even if it doesn't work, you know, keep the presentation intact. And we'll talk about that as well, how to do that, okay? So that's and also the Rails lecture is not going to happen. Basically, we don't have the time. There was not really enough interest, but if I'm, again, open to helping people individually or whatever as we can find time to do it, okay? All right. So here's what I want to cover today. I want to talk about scaling versus performance. What's the difference and how do we do it for mobile products? I'm going to talk about typical kinds of scaling problems that occur and why they occur. I'm going to talk about techniques to handle this on the client. I'm going to talk about techniques to handle this on the server. It's going to be pretty high level, just an introduction to the topic as we've done before, to give you an idea of what's, you know, what the issues are and how to think about it. You know, if anybody remembers when Twitter first got, you know, really busy and then started crashing a lot, they were having scaling problems. Scaling problems are among the most difficult problems to solve when you're engineering a system like each of you is doing. So when Tim, with great panache, said of Happy Sad, it's ready for 1 million users, I told him I had to swallow a little bit instead of putting some cold water on it. But it's an interesting question. Is it ready for 1 million users? And we can sort of do a little bit back of the envelope calculation to think about whether it is or not. Okay? All right. Can somebody put the light on so this thing is illuminated? And then anybody, I'm going to just wait 15 seconds, can guess what I've drawn here?
You guys walk me to a bar.
Restaurant. Okay, and?
Why the long
Oh, yeah, exactly. No, this is a drawing of the cafeteria in Shapiro. And these are people waiting in the cafeteria, right?
Einstein's.
Yeah, Einstein's, yeah. I mean, obviously, somewhat.
Clearly.
What?
Oh, yeah, these Einsteins.
Okay.
What happened to their hands?
Their hands?
They're holding.
They were in Vietnam.
Sides.
They don't want to talk about
Okay, so my question is, when you get there, sometimes there's a huge line.
Oh, okay, now it looks okay.
Better now?
Yeah.
You get there, there's a huge line, right?
Yeah, fixing
Why?
that line keeps really deep.
What's wrong?
Fixing that line.
Helped it, now it clicks?
Yeah, now
I mean, I did put the bookstore in and all that stuff. I took some creative freedom. But there's a long line. That's a scaling problem. So who can say why that happens? What circumstances cause a long line to form? And as specific as you can get. Yes?
One register.
One register, say more.
So like.
Why does one register cause a line?
Because that means there's all customers have to go through that same point to get their food and pay for their food.
Yeah.
So if you have a lot of people who want to do that at once, then you're going to have this backlog. But if you have multiple registers, that means people would split the line. So
Yeah.
each line is respectively shorter.
So you mean if I put in 10 registers, there'd be no line?
I mean, it would be like one person at most.
Okay.
Or
Any other
flow.
points? Yeah.
If people are using credit cards and not just like Red Ice meals and they're
Yeah.
using cash.
Yeah.
that's-
So in other words, that's causing, on the assumption that taking credit cards takes longer, which it may not. But you were saying if the service time it takes to handle a transaction is longer, you may form a line. Yes? Yes.
Simply enough, there's more people on campus.
Yeah.
Maybe it's like a holiday, maybe a new person from like Brazil or something.
Yeah.
summer program. Yeah, maybe one of those things.
Brazil.
If that happens.
We get within people, you know. Yeah.
It also depends on what type of food each customer orders. Some of them
Yeah.
are just pre-packaged, so you can just
Yeah.
get it ready to go.
Yeah.
Other ones, if they want like bagels with toasted cream
Yeah.
cheese with
Yeah.
lox and extra super stuff, it takes a little bit longer.
Right, exactly.
Yeah.
If you, they aren't fed it efficiently.
Yeah,
So
that's
if
big.
somebody who wants a lot of stuff, cooked stuff that's
Yeah.
standing in front of you,
Yeah.
you just want that little bottle,
Yeah.
you're gonna be mad, but you're gonna build up a line.
Okay, yeah, but I mean, so you're all focusing on the transaction. Yes.
There's not enough equipment or room, there's not enough employees working at one time.
Right, okay, yeah. But there's also the fancy of what people are ordering, right? I mean, what if it turned out, well, what if I told you, you're managing the cafeteria or the coffee shop, and I told you tomorrow there's gonna be a conference and there's gonna be twice as many people on campus as usual. Prepare. What would you do to prepare?
Extra coffee?
Extra coffee?
If it's a conference, most people probably just want coffee,
Okay.
so I'll have extra coffee ready beforehand.
So in the back room, I'm gonna put more bags of coffee here,
Yep.
okay? Okay, what else? Yes?
I'd probably change that. I'd probably put more coffee out front, so it's easier for people to get.
Like sometimes they have coffee machines over here, right?
Yep.
Yep. Why? Because now you have more stations servicing the coffee demand, right?
And then
So
I
if you
also-
assume there was coffee, then you might do that. Yep.
Right. I'd also probably definitely add another register, have somebody, or have more staff working.
What if this register was, sometimes I have a register here, but let's say this one could do credit cards. Would that be a good idea or a bad idea?
Bad idea.
Bad.
Why?
Because if somebody who has a credit card lands up there,
Yeah.
he's just gonna be standing there for no reason, and be like, oh, what? And then going to get in the other
Yeah.
line.
Right. Okay, yeah, that's true. So anyway, so these are all scaling problems, is what I'm illustrating here. And the way you solve these scaling problems in the discussion is the way you solve scaling problems in the system. Okay? You look at the traffic that's coming in, and you ask yourself, what are they going to need to do? So there's a question of what the nature of the traffic is. If you measure and you discover that 9 out of 10 people that walk into this line are getting coffee, well, then obviously you may want to make another coffee spigot. If you find that 9 out of 10 people, that the queue forms here because people are ordering bagels with cream cheese, toasted a little bit, and a little bit of salt on it, you might add another person working on the bagel line. It's all very common sense stuff, but I just want to illustrate that this is essentially how you go about thinking about scaling the computer system. Exactly the same way. Okay. So one thing to think about is that scaling the way it is used and the way I'm using it now is different from, or is related but different from response time or performance. Okay. Scaling is specifically has to do with the amount of X's, whatever they are, that your service can handle. So in other words, if your mobile app has no server side, then you don't really talk about scaling. You talk about performance, you talk about response time. The thing can be slow, but it's not a scaling problem. The scaling problem is when you have a lot of clients, i.e. Androids, going at a single point, asking for requests, and those requests take time to service so that they end up waiting. And you end up blocking your user interface or displaying the wait person. So the question is, how do you handle it? Before I get to that, let's talk a little bit more about performance. Now, interestingly, on a website, like when you're sitting on Facebook, right? Then there's an element of performance in how quick the menus drop down and how quick the pages change and all those. And they do a lot of JavaScript on the client to make it fast. In that world, and the same thing's true with your Android, the expectation of the user is that things are really, really fast. Okay? People are very intolerant of delays where they don't see something happening or where it doesn't make intuitive sense. So you can do a few things. You can help make it make intuitive sense by giving them a wait cursor or something that says downloading bottle 1, bottle 2, bottle 3, bottle 4, and simply without changing the scalability of your server at all, you've given them something to watch and you've given them a mental picture about why it may be slow. And just by doing that, you reduce frustration, because that's what you want. I mean, if nobody notices slowness, you don't have a problem. It doesn't matter what part is slow or how you are making them not notice. Another way to do that is by misdirection. Draw their attention somewhere else, distract them. You often see websites where they put up a box where there's some kind of animation, where something funny is going on. where maybe you give them something else to do, and in the background are working on what the slow process is. So there's ways of distracting or misdirecting, and all those things are totally part of your toolkit in trying to deal with a slow performing system, right? So you can fool the user to think the app is faster than it is, you can give them feedback and so on. But in truth, what you need to do is put any, this is true of a website running, being driven by something like Rails or something else, it's true of your Android app. Anything that's slow has got to be put on a background thread of some kind. Because in both cases, what you end up, if you don't do that, is with a locked user interface, an unresponsive user interface. That's the worst possible thing. So, background threads are a basic tool of the thread. I know you guys are doing a lot of background processing on Vogel. We're not doing it yet. Giraffe is probably full of background processing as well, right? Because it's all background. We got to jump into that. Okay. So that's sort of a little bit about performance. Now there's one thing I want to mention, which is that this is kind of a principle which is important to try to implant in your head, which is people say that the worst sin in software engineering is optimizing too early. Who can take a stab at what the meaning of that is? Yes.
Well, sometimes you develop something and you focus, like say you spend 2 hours on optimizing it, you get to work brilliantly and it's like really written, perfect and efficient enough.
Yeah.
And then tomorrow you need a new feature which makes the old feature redundant.
Yeah, that's one scenario. Yeah.
Maybe this is not exactly what you're thinking of, but a lot of older software was written like that to optimize threading and memory allocation and stuff like that.
Yeah.
But now that operating systems are advanced enough to do it for themselves,
Yeah.
these old programs have these useless optimizations that make them run slower.
Right. That's true. Yeah.
One thing I would think of is that since you just launched your app, I guess this is the ideal scenario. You
Yeah.
don't know what you need to optimize for,
Yeah.
what people are going to complain about,
Right.
what people want. You want to get the user feedback
Yeah.
first, then optimize.
Even without user feedback, I mean, the germ of what you're saying is that it's very, very common to be wrong about what you think is slow. Any of the 3 projects spent any time optimizing on anything, something that was slow that you wanted to make fast? Yes, what?
Just a lot of the threading stuff.
But what was slow? I mean,
Like say this is what we were doing yesterday, so we built the maps
Yeah.
and the maps trying to pull the 100 latest bottles in the current view.
Yeah.
And it was initially taking a lot of time to loading stuff up, so
Yeah.
it's going to take a lot of time trying to make it faster.
Right, right. So that wasn't optimizing too early, that was optimizing time. In other words, you didn't build that complicated threading ahead of time, assuming that the map would be slow. You waited until you saw that it was slow. But then even then, did what you tried the first time make it faster?
No.
Why not? Do you have a theory?
I tried it for a long, long time, like I got different sets and stuff to work, but sooner or later, like, they'd crash.
Okay, so it crashed, but the question is, once you got rid of the crash, did it go faster?
Oh, yeah.
Okay. Yeah.
I guess maybe this is an example of optimizing early. When we called the database, at first we called the entire database
Mhm.
and then cursed through to find rows we wanted.
Mm-hmm.
And then later on, I went back and changed it so that the actual database query was smart enough to get you exactly what rows you wanted. You didn't have to
Yeah.
parse through, you just, for each row in the cursor, do the same thing.
Which is interesting because it's not self-evident at the start what would be faster, right? Because you could argue that you have to do a call to the database over and over again, going over the network, dealing with network delays and so on, that it would be more efficient to pull things over in one shot and then do all the work on the Android.
Oh, I meant the local database.
Oh, you meant the local database?
Yeah, and I have no idea if it made it faster in practice, just it's
Yeah.
cleaner in theory.
Yeah. Well, so did anybody else have a thought about that? Any thoughts about that? Yeah. Yeah, I mean, the temptation always is to do something fancy, to do something elegant, to argue about, if you do it this way, it's going to be slow. No, I think it's going to be okay. And that's when you sort of deploy this slogan, which is, optimizing early is the worst sin. There's one more reason, which is that optimized code, almost by definition, is more complicated, which means it can be more buggy. And then, therefore, if you optimize it and then you have a bug, it's more difficult to fix. So that's another reason. Another reason is to implement things the simplest possible way. Don't debate performance, and then measure. And then when you measure and you see that something is slow, and you can actually put your finger on it, say this is taking too long, then, and by the way, the user can see this, then you worry about optimization. You can spend days making this operation fast because it's done in a loop 10,000 times, until you realize that that operation that's done 10,000 times in a loop is only done once when the server boots and then never again. And you realize that it doesn't matter. And so that's the principle. Optimize the earliest, the worst thing. So optimization is the search for bottlenecks, basically. A bottleneck being a narrow place that everybody tries to go through at once, right? And you can have a narrow place that nobody tries to go through it, that doesn't matter. Usually when you find a piece of slow performing code, it's because there's a bottleneck, and your assignment is to remove that bottleneck. Remove that bottleneck by either allowing more people through at the same time, or finding a way. When I say more people through at the same time, what I mean is a bottleneck might be that I'm doing a loop 1,000 times, and each operation is slow. So I can either find a way to make the operation faster, or I can find a way to do fewer iterations. And what you find is that if your product is slow for whatever reason, then you can, with a little bit of measurement, identify a whole bunch of places that are potential bottlenecks. And then the question is which one to go fix, because you can argue each one is a problem. The way we implemented this data structure is wrong. The way we're accessing the database is inefficient. The way we're calling the server too often. We're doing too much network I/O. We're garbage collecting too often. These are all problems. Which one to do first? And so then the art becomes to measure, so you know which is the one that's having the greatest impact on performance of your product, and fixing that. And when you do that, what you find is another one of the bottlenecks becomes the worst bottleneck. And then you go after that one. And that's exactly the process. And at a certain point, if you measure every time, you're going to get to the point where you realize that the product is faster than you stop.
Are there tools for identifying where the bottlenecks are as an eyeball?
There are lots and lots of tools. It's a very important part of the software development kit for any platform. I haven't looked at Androids, but I know Java has tons of them that will draw, they're called heat maps. They draw a graph or a kind of a histogram of all your code showing peaks and valleys where the code paths that are visited more often, or the ones that are the slowest. It'll say, if you have method A called method B called method C called method D called method E, and that whole thing is slow, it's going to help you find out which of those ones is the slowest. It could be that the lowest one is fast, it's one in the middle. And it's going to help you find that one. You find the method A called method B called method C, which called method D 1,000 times, who called method E, which called method F. The 1,000 times is the problem, and you have to find that. There's a basic question with measurement always is, it's kind of a version of the uncertainty principle. To what extent is measuring, putting the measurement tools in, going to be slowing down your product? Or to what extent does your product behave in its natural way if you enable all the different kind of metrics? So that's always one of the trade-offs. But yes, there's plenty of tools. And people sometimes build their own. But the important thing is measure. Don't assume because you're so often wrong. And because optimizing introduces bugs, and optimizing is hard. Okay. So now let's talk about scaling. So that's performance. That applies to an app that doesn't even have a server. And that's all good principles to follow. But you can do a wonderful job with that, or you can do a terrible job with performance of your app, and still have a system that doesn't work at the speed that the users want it to. So scaling, as I implied with that diagram, is basically has to do with how many X's per minute can I do? For example, how many logins, how many fetches of bottles, how many swiping to the next fashion photo, how many of those can I do? Or it may be, how long does it take to do A? How long does it take to log in? That can be the nature of a scaling problem. And finally, it can be, and as I said before, rather, it has to do with the load of the servers. So that's kind of at a high level what scaling is. And scaling is a huge and important problem. It's like in the catalog of difficult problems to solve as a software engineer, it is among the most difficult and the most important. I mean, Twitter almost went out of business because of scaling problems. Google Plus, you can be sure that they spend massive amounts of work ahead of time to ensure that Google Plus would scale, because if it didn't, it would be another black eye from Google, which would affect their stock price and cause a lot of people a lot of misery. So they focused a lot on scale. Now, of course, Google and Facebook and Twitter are very good at scaling. They're like among the best. You put in there also Amazon and Microsoft among the best, and it's very, very, and a lot of the techniques that are now kind of part of the standard toolkit were invented and discovered and you know, tested and optimized at these in these different companies. Okay, so so what are some of the patterns that you see? Well, basically, it has to do with load on the servers, as I said. So the first possibility, of course, is there's just too many clients that are asking the server to do the same operation. So whatever the operation is, it's slow, and everybody's asking to do it. Therefore, they have to get in line and take, you know, and wait their turn. And that operation for a certain Android becomes a slow one. That's one scenario. Another scenario, which is similar but different, is an individual Android is asking to do certain operation too often, over and over again. It's a different scenario because the techniques you use to address both scenarios are different, okay? And then the third general scenario is simply that the operation, whatever it is, logging user in, is too slow, okay? Those are kind of the general patterns that you see, okay? So how can you address those kinds of patterns? Let's take one of them. Let's take the first one. Too many clients are asking the server to do an operation O. Can any from the three products, is there an example you can cite?
I'm really worried that get the 100 bottles in this particular box
Yeah.
is called too often and would overload the server.
Okay. Is it called too often by an individual Android, or is it called, or is it basically, in other words, when will an individual Android call that operation?
Every time you pan or zoom the map.
Every time you pan or zoom the map. And do you think users will be panning and zooming the map often?
Yeah.
What percentage of users do you think will even go to the map?
100.
99. Okay, all right. And you think that the first thing they will do is pan and zoom the map?
Yeah.
Okay, I'm not arguing against it. I'm just saying that's the kind of questions you ask in thinking about how big a problem this might be.
Okay.
Okay? So because you can have an operation that nobody ever does, and then you don't really care. Or
Right.
once in a while people do it. This is a central operation, a lot of people do it. Okay. Now the next question I have for you is, so you have a problem that, hypothetically, too many people are going to be zooming and panning the map, and that's going to cause each individual Android that's running, that has an active user, to be sending this request.
Mm-hmm.
What are some ideas that you could, let's say you actually measured this was a scaling problem.
Mm-hmm.
What are some ideas of what you might do to address that?
I have a few.
Anybody else on your team? Yes?
One idea could be that it would take, once percent it looks at your local, like your area, and it takes like certain pan and zooms,
Yeah.
and it stores that in a local database, so it doesn't make as many calls.
Yeah.
So it still may be making calls, of course, but not as many. So if you do go pan like a little to the left,
Yeah.
well, it's already in a separate, like some sort of local database, so you
Yeah.
can just pull that information instead of pulling always from, just directly from the server.
Right. Do you have a handle on how big that, how much, is it a big data structure or pretty small?
I just don't know how to like visualize how that would work out.
Well,
It's easy, like what, with the implementation will be like, right now what we're doing is we're pulling for, say, the top right to the top left, to
Yeah.
the bottom right to the bottom left.
Yeah.
And I have the width and the span of the latitude and longitude being displayed.
Yeah.
All I do is I triple the width, and all of a sudden I have 3 times the size of a box already being
Right.
stored, so if you pan and tilt,
Yeah.
the query is still being given, never mind.
Pardon?
I realize the query is still going to be given, because the query is based on the current center and so on.
Yeah, but the question is, how big a structure is this?
What is
I mean, it's an interesting point about basically trying to cache calls. And I don't, the trouble is the way you have it now, it's latitude and longitude. Each individual person would be totally different. But if you did it by state, if you instead allowed people to say, I want to see everybody in to Massachusetts or New York or whatever, that's just 50. And you could, and in the country, say 300 different locations, you could just cache those easily.
Even by state.
And then, just up every time it gets updated, you just update those.
But let's do a little back of the envelope calculation of how big a structure we're talking about. So there's basically an entry in this table for every point,
Yeah.
right? Every little symbol on the overlay. And there is, and with each point is stored what information?
A message.
Overall. Huh?
A message.
a message,
There's a
some
latitude,
text.
a longitude,
Yeah.
a user ID,
Yeah,
an int, who's defining your emotion,
yeah.
and
Message.
longitude, message,
And time.
and time.
Okay, so like in the world of little computers, that's next to nothing, I would say. It's very, very small. What is, when the system is working, here's another back of the envelope calculation you can do. Assuming, and you can go crazy with this sort of modeling, but assuming that the product is being used at Brandeis, by 1 out of 10 people.
Yeah.
And how many points would you expect to see on the default size grid? 10?
Well, we said 100.
Yeah.
You can narrow it down to whatever you want it to be though.
Explain 100. 100 is what?
The query says, given
Oh, I
the
see.
Zoom we're doing right now,
Yeah.
give me the most recent 100.
So you get a radius of a rectangle of 100 points. 100
Yeah,
close.
a rectangle with 100
100
points.
all those
100 points,
Hundred
yes.
most recent.
At most 100 points.
At
Yeah.
most 100 points.
Yeah.
But what is the default size of the rectangle?
The screen size.
No, but I mean physically, is it? I mean, totally vague numbers. Is it
No,
the
it's
size
just-
of the whole campus?
It doesn't work like that, the
Doesn't work
rectangle
like
is defined by your current view, so.
No, so like in the default Zoom,
The
your first
default
one
Zoom.
on the dashboard,
Mm-hmm.
what is the zoom level? And given that zoom level, how many feet or miles wide and tall is that?
I wouldn't say it essentially depends on the default zoom, like coming back to the thing, say I've panned out or panned in or whatever, sorry, zoomed out or zoomed in or panned here and there.
Yeah.
It'll look at the center and it'll look at exactly how many latitudes and longitudes are being displayed. And within that set of latitudes and longitudes, only that are being displayed looks at the last 100.
Right, right. But it could be much less than 100.
It could be,
Yeah.
right now it is much less.
Okay, all right.
Mm.
So,
We might have to
so
make
it
that.
sounds to me like, so this will take a little bit of measurement. This line of analysis, quote unquote analysis, will tell you something. But gut level, you might flip it around and say, give me, grab 100 or grab n that are the closest to this point or something like that. So you get a rate, and then you keep that good as long as you can while he pans and zooms. Because 100 on the Brandeis campus, if you assume 10% use, how many people are on campus when it's busy?
3,000.
It's
3,000.
historical data though.
It's historical, okay, so it's 300 people, and
You'll always-
multiplied by
always have
3, it's
100.
1,000, okay, so it's 1,000 points, it's a sort of random guess when it's relatively. So, if you got 100, you probably have a pretty big radius. So you might look at it that way. And also, you might also measure another thing you can do, which we heard, I think, from Ed Baraf, is instrument your product, right? In other words, what about if you actually collected some data, and this is probably not by Thursday, that said, how often are people zooming, or how often are they getting less than 100, and report that in the database, so that you can look and see data from actual use and figure out what's going on. Okay. Let's see if we can find an example of operation Q is 2 time consuming for the server to satisfy. Does anybody have a server request which is they expect will be relatively slow? Yes?
Pulling all of the items from our server. Well, at this point, we're starting to pull batch sizes, but originally we were pulling everything. in
Right,
our
right.
server.
So originally, you might be pulling a huge amount of things from the server. And that has a double-edged problem. One problem is that the client is slow. The second problem is that if a lot of clients are doing that, the server is going to become a bottleneck,
Yeah.
right? So what did you do to optimize that?
We created by we, I mean you, created a query to be able
You
to,
specified it, I merely implemented it. Yeah.
to be able to pull a certain amount of items in a certain department with certain, well, in the future, with certain tags.
Mhm.
hopefully.
Right.
But for now, just being able to pull a certain size
Mhm.
that haven't been looked at before.
Mhm.
Which is important.
Yeah, another thing that Global is doing is that we're not pulling the images. I mean, that's kind of a scalability choice, even though we didn't call it that, right? There is a database on Global that keeps track of, what dresses Peter looked at, because
For your wife.
dresses sometimes.
For your wife.
But that database does not include the images. If that database included the images, we would be creating a scalability problem, because now, every time this operation was done, to say, give me 10 items to show Peter next, the images would be transmitted. So it was a scalability choice, actually, to do this. I'll come to it. which is that the request for the image is being handled by one server, i.e. Amazon server, and the request for who saw what is being handled by another server, the Vocable server. That is a core scalability design. And that actually was subconsciously why it was done that way, because we didn't express it as scalability. Okay. So let's go through basic techniques for scalability. And it's interesting because this, the example that Todd gave, caching is like the most basic thing. It's a super important technique that applies to everything you do as an engineer, software engineer. And it's pretty simple. This is all, I say pseudocode because I haven't tried to compile it.
Server proxy.
Say what?
What's server proxy?
I will explain. I will explain. So without, this is a pretend method in the Vocable app that gets the item price for a certain item number 14. Okay? And it says, okay, my base URL looks like this. And you guys have a different name. It's just the class within Vocable which does the server calls. So we tell the server or helper or server proxy, get the item at this URL. We take the URL base, which is this. We concatenate it with the item, and we ask it. It returns, typo, it returns an item, and we return the price. Okay, very straightforward, totally clear to everybody? So here's how we do caching. We create an integer called cache item. We create a float called cache price. We have the same exact method as before. We do the same thing as before, but the first thing we do is we check, is the item requested the same as the item that was cached? And if so, we return the cache price. We never talk to the server. Otherwise, we ask the server, we record what the item was, we record the price, and we return it. Okay? Is this crystal clear, brain dead simple to everybody? Anybody at all puzzled? Okay. So the elements here of a cache are, so what is caching? Caching is simply putting some information closer or more handy so that when you ask for it again in the future, it's quicker to get. That's the principle applied everywhere. So you got to remember a few things. You got to remember the key, and when I say the key of the item you're looking for, okay? And then you got to remember the value that was returned, because if that key is requested again, you can just return the value without doing the hard work to get it. In this snippet, which is the key? Mike, go.
Not sure exactly.
Okay. How about R10? Which is the key in this example? Huh? Okay, let's go through it. So I'm asking get item price for item ID, and I'm saying, oh, is the item ID the same item I asked for before? If so, I'm going to return the price I remember from last time. If not, I'm going to ask the server, which is slow and expensive. But once I get the answer, I'm going to remember the item for which it was, and I'm going to remember the answer for which it was, the answer I gave, I'm going to return that. That way, if somebody asks next time for the same item, I'm going to fall through here and just return this answer and be very fast. So in caching, there's two things you have to do. You have to notice what you have to look at the key for the item you requested, and then if that item with that key was requested before, then you can look at the answer you gave last time. If it wasn't, you do the slow operation to get the answer, i.e. call the server. You remember the item for which, the key for the item you're asking, you remember the answer you gave, and you return it. So in this code snippet, which is the key?
The cache price.
It's the item ID. Okay, the item ID. And caching always has a key. There's a key and a value. What was the key? It was the item. It was the point. It was the price. Sorry, it was the person. It was the user. It was the fashion. Whatever it is. And then there's a value. The value could be the image. It could be the price. It could be the lat long. Whatever it is. If I ask for the same item again, the same bottle item again that I just asked for, then I can remember from before what was the lat long that I returned and return that. Yes.
So I'm just have a question for cache item. That's just an integer value, correct?
Yes.
So what if?
Yeah.
So what if they're both the same? That's fine. But what if the price of one of them changed? Like what if the actual item price changed? Then your
Very
cache
good.
item is
Excellent.
destroyed.
You're hitting on a very important point about which I was going to ask, but you beat it. Does everybody understand the question? Does anybody have an answer for the question?
Wait, I'm not sure I understood the question.
Pardon?
I'm not sure I understood.
The question was, what happens if an hour later, because Amazon actually warns about this in their API doc, prices change all the time. An hour later, there's a sale,
Oh.
right? I'm gonna ask for this particular, pair of shoes, and the cash price is wrong, right? Yes?
You set it, you set a little expiry, so every time you're gonna pull the item, you're also gonna pull the time and
Mhm.
mark it.
Mhm.
And when you're checking, you're also gonna check it against the time.
Absolutely, that's one way, that's one key technique. The other key technique is yes,
Well, instead of maybe getting the item ID number, you can get the actual item, just compare the prices. So it's like the prices are wrong then.
yeah, but then you haven't gained anything,
Oh,
because you're
yeah,
still talking
you're
to the
right,
server,
you're
right?
Yeah.
But, yes,
Maybe you return the cashed price right away,
yeah,
then you set up a tiny thread to like check it for you, and if it's different, like dynamically update it.
that's a more advanced technique. There's another basic
But if
technique.
you're already checking if it's different, you're already looking at what it is on the server.
And it's the user responsiveness.
Yeah.
It gets the answer quicker, even
And
though
then
it's
it
updated
changes.
then later.
Like, as they're looking at the dress, suddenly the price changes. It's a good technique. But another basic technique is if the change in the cash item is under your control. In other words, if this wasn't Amazon, but it was a payroll system, and another user of the payroll system changed somebody's last name.
Push it,
Huh?
push it.
Well, then, the one who writes to the database, the form that says save last name, their job is then to tell anybody who's caching the last name that their cache is wrong and get it. So the term is called cache invalidation and cache consistency. So you have a cache consistency problem when the cache is returning information which actually is invalid, and you have cache invalidation, which means some part of the system tells the cache what you thought was the price is not correct anymore. Yes?
So as soon as that's updated on the server sends out that message to whoever's listening to whatever device is
In
listening.
the scenario I just described?
Right.
Well, in the scenario where I own it's the payroll system and I'm changing the last name,
Right.
it's not so much that the server sends out the message, it's that the piece of code that's updating the last name both tells the server and tells the cache system.
Okay.
Anybody who thinks they know the last name of employee 41, think again, your answer is wrong, you better check with the server.
Right. Okay.
And so that assumes that, and I'll get to this in a second, that assumes that the caching system is somehow a global facility. In this case, it is totally elementary implementation. The cache is just a private variable inside of the class. So obviously it wouldn't be possible, but as I go further, you'll see. But this is a very elementary technique that is incredibly powerful, that should be in your toolkit, because it's 3 lines of code, and sometimes it can make a massive difference in performance. What does it assume? What is the assumption it makes about the access pattern? That if it's not true, this will not do a thing. Yes?
But the item ID never changes, the key never changes?
Yes, but there's even a more basic thing. Yes?
But this is what people are interested in seeing.
Say again?
But this is what people are interested in seeing.
Right, but can you, in the right general area, any other ideas, any other calls here? You're assuming that people are looking at the same item's price multiple times in a row. If I look at 41 and you look at 42 and you look at 43 and I look at 41 again, this is not going to help you.
Ooh. That could have been really bad.
Right? If I look at 41 and you look at 42 and somebody else looks at 43 and then I look at 41 again, it's not going to help me. Why? I saw your hand up. No?
But you're on your own app, and
Yeah.
that's right in the app, so you are looking at the same thing twice.
No. I mean, because I could look at this dress and then look at that dress and look at that dress and then come back and look at this dress.
Okay, so it's all on the same Android phone.
Yeah, let's say. So
Okay, yeah.
this cache is not going to help me at all because, item ID is going to be 4 and the price is going to be $100. Then it's going to be 9, it's going to be $200. That's going to be 4 again. I don't know, right? So this cache should always have an assumption about the pattern of access.
Well, we don't know where the item ID is coming from. Your code doesn't tell us it's generating a new item ID.
Well, I mean, the item ID is the key within the app that refers to a particular item.
This code only saves the last
depends on how
item
you-
viewed. Once you view a new item.
We don't know whether his last view is the item ID, because from what you just said, that's what we come to, but this code doesn't tell me that.
But this code does have an assumption that it only caches if the sequence of calls to this method called get item price. If there's not 2 calls to that method in a row with the same item ID, the cache function in here is not going to do anything. Because if I call this method with item ID 5, then call again with item ID 5, that's gonna be fast. But if I call with item ID 5 and then 6 and then 7 and then 8 and then back to 5, it's still gonna go to the server.
Oh, okay. Now
See, so and this is like a one, this cache is very simplistic, but sometimes if you know that that's the pattern of access, which is very common, can be, and it would not be a bug, then this kind of technique, which sometimes is called memoization, because you're making this method have a memo that remembers the last thing you returned, is very useful. Yes?
So it would be better if you had like a cached array list.
For example. So, okay, that's the next level, is exactly that. You create a instance variable, which is a hash map or something along those lines, which maps the key, the int, to the float, the price. And very similar code, except instead of just picking up the variable, I look it up in the hash map. If it's there, I return it. If not, I create it, i.e. I ask the server, right? And then I put it in the hash map for next time. Now, great, life is good, right? Because now if I have this access pattern 3, 4, 5, 6, 3, it's going to remember the price for 3. Yes?
So I want to answer the question of what bugs are hidden in this code.
Yeah.
We had a very common problem where we would do something conceptually like this, maybe not with caching, but we call the class that had this multiple times. You know, like once for each activity. So the hash map wasn't being shared between different, at different points.
So you have different hash maps, one for each activity.
Like once for each instance of the object, of which there were several.
Because there was one for each activity.
Yeah,
that's a good point. So that's a singleton would help there to make sure you have only one. Yeah, we had similar problems in the Vocable, the idea that each activity, not only is it separate, but once you're at the next one, the previous one can be garbage collected. And then suddenly your cache disappeared, right? Yes?
I want to address the scaling problem. If you had like, I don't know, 1 million things in your database and it has to, search to see if it contains that key, wouldn't that take a long time?
That's a good point. In other words, well, it's not a search, it's a hash map. Did you take the data structure course?
No, I haven't.
You know why it'd be fast. But it would be fast, but there's still an issue. There's a point of diminishing returns. There's a point at which the cache is taking up so much memory or has gotten so big that looking up in the cache is actually slower than just asking the server. It can happen. That's something to think about. Yeah.
I was saying now we're building up an optimization problem.
Yeah, exactly. So that's a trade-off. Another thing that anybody else see an interesting question that has to be answered here?
What assumptions does this kind of caching make about the scaling problem?
No, but that's a good one. But what I was asking was thinking about was simply how big should this cache become? Because the way I wrote it here, it can grow infinitely, right? I mean, especially if for some reason the keys that are fed into this are unique every time. Like, what if you said, I'm going to use a cache where the key is the time of day, and the value is I don't know, the weather, except the time of day always changes, and so eventually this cache is going to be humongous, and nobody ever asked me looking at the old stuff. Yeah.
Yeah, at some point you have to ask yourself, do I want this to be a hash map or do I want it to be like a database?
Right, exactly, absolutely. Because a database can be used legitimately as a cache, by the way. I mean, a cache is just a faster way to get something you get often, to save the trouble of doing it in a slower way. Did you have a question?
I was thinking of like, what if you only implemented this on things that you like, because you're assuming if you dislike something, you won't see it again, so there's no point of caching.
Absolutely right, absolutely right. And the other thing that's interesting about all these schemes is that the callers of this method are blissfully unaware as to whether this cache is going on or not. So you can put in a dumb cache and put a smarter cache in, or remove the cache, and everybody is unaware of it. It's totally encapsulated in this one method, and that's really good. Yeah?
An optimization solution that I came up with is have a parallel hash map that for every item ID builds up how many times it's viewed. And once that new hash map comes to a certain size, say 100, it'll constantly delete the old hash map and just set it to the last 100.
That's in other words, you're creating a. Now, what happens when a new thing comes in? Do you put it both in the old and the new? I mean, what do you do?
Interesting question. I think we need a timestamp.
Yeah. So I mean, there's various techniques to deal with the problem that it grows infinitely, and that's one. More conventionally is that there's simply a timestamp with each entry in the hash map. So when it's time when you hit whatever threshold you care about, you can just go through and delete all the old ones. Or you can do whenever I add one, I simultaneously delete the oldest one, so one for one. That way, thereby keeping the thing at a certain size. There's any number of techniques, but the key, sorry, do you have something?
I was just gonna say one more technique.
Pardon?
I was just gonna give another technique.
Go ahead.
Where you can have a hash map that has size 100 and fill it up, and have another one that has size 100 and fill it up with another one. And when you search, you have to search through all the hash maps, so there's a little slowdown. But then you just throw away, the last. You keep 10 of them, keep when one fills up, you throw away the 10. That way you don't have to search through it, it's just there.
Well, and then, absolutely, and then of course there's one more thing, which is least recently, or oldest, throw out the oldest one, the one that hasn't been accessed in a long time. In other words, don't record the timestamp of when you created the hash entry, the cache entry. Mark the time when you accessed it last, because it could be a very old item in the hash in the cache, which everybody's constantly accessing. So if you record the time of last access, then you can delete stuff that hasn't been accessed in a while. That's another idea.
Let me make a little, how many people take the data structures class? How about the 180 algorithms class?
Little plug here.
Oh, yeah, a plug. Because this is exactly the kind of stuff that you deal in 180. You've got something which is a non-standard algorithm. You want to have a hash you can look up quickly. You also want to throw things out. So in this case, you'd mix a priority queue with some kind of like open or closed hashing. And it's something you're not going to find in the standard collections. But if you know enough data structures, you can write it up yourself. It's really fun.
It's really fun, especially when you see with a few lines of code, your product gets 10 times faster.
Yeah.
That's the kind of wins you look for. And that's the whole thing about optimizing early. If you wait until you know what the problem is, and you can show what the problem is, sometimes the solution is super easy. And Java has such a massive library, and once you go beyond the library, there's massive other open source things you can use. That all these things just go out of the Stack Overflow or Google, and you'll find code samples, libraries that want to do this in arbitrarily complex environments. Sorry? Did I hear it?
No, it's stretching.
Okay. All right, next. Let's see. I have 11 o'clock. Should we take a break? Everybody can go take a quick 5-minute nap? Power naps. Power naps. Okay, see you in 10 minutes. Power naps.
No, we decided not to. You wanted to do something.